Welcome back. In the last video, we turned a single image into patches. And you'll notice that I've got a different image here to the last video. It's now of sushi, but that's because I took a little break and just reran all of my cells again. So if we do that, it's going to load with a different image here just to verify that the code still works. So while that's running, let's start to create a heading. We're up to section 4.3, and that is creating image patches and turning them into patch embeddings. Now, you might have already jumped ahead because I've revealed a few hints over how we're going to turn our images into patches using PyTorch layers, and then of course turn them into patch embeddings. So there we go, we've got another image here, steak turned into patch. So we see the overall premise of what it's like to turn an image into patches, but now we need to flatten our image into a sequence, but we also need to turn it into embeddings. So we can do both of those steps with inbuilt PyTorch layers. And the hint that I gave you, oh, there it is. I guess this is a GIF, it's going to keep playing. .gif, that is, not GIF. Well, it is kind of a GIF because it's a beautiful animation. But let's just hide this for a second. Back in PyTorch Computer Vision, we had a look at the CNN Explainer website. So let's jump back into that. So if we need to create patches, if we need to turn each one of these into an embedding, what does that kind of operation look like? Because we looped through the image's height dimension as well as its width dimension. If we go back to the CNN Explainer and go back down to a convolutional layer, we've got different hyperparameters here. So if we play this, what's happening? Let's change the input size to be 7 by 7. And we'll set the kernel size to be, 2 by 2 is good enough. And a stride of 2 as well. Now let's play and see what happens. Oh, can this not work? Maybe we make this 1. You see the red tiles, how they're sliding across the image? Is that something similar to what we want to do? We want to slide across our image and create patches. Perhaps this could be considered, this input 7 by 7 could be considered our input image. And then over here, these could be considered our patches. So how would we recreate this with a convolutional operation? So if we go back here, if we wanted to make a 16 by 16 patch, and we wanted to use torch nn conv2d, what could we set the hyperparameters to? So we've got in channels, out channels, kernel size, and stride. Well, let's go back to the keynote. Do we have that animation here? Yes, we do. So this is what we want to do, right? We've seen, oh, excuse me, little spoiler alert as well. Let's play this animation. So we want to cut it into patches. We've seen how to do that with matplotlib. But now how do we turn these into embeddings? Well, we could use a conv2d layer and set the kernel size to the patch size. So we've got a window here, and then stride to the patch size as well, so it slides over. And then we turn each of the patches into convolutional feature maps, or in other words, embeddings. And then if we wanted to flatten to a sequence, well, we could use the torch.nn.flatten layer. So now we've got convolutional feature maps act as our patch embeddings. And then we've got other embeddings to add, but we'll get to those in a second. So let's jump back to Colab, right down here. So perhaps we could create the image patches and image patch embeddings in a single step using torch.nn.conv2d and setting the kernel size and stride to patch size and stride values or parameters to patch size. Because if we go back to the CNN Explainer, that will give us, if we set this kernel, this red square here, to 16 by 16, that'll be the kernel size, and then set the stride to 16, well then we'll get a patch, a patch, a patch, a patch, and so on. Of course, this image is not to scale, but if we get out of these two and go back to here. This image is to scale. So we get kernel size 16 by 16. And then the stride, if that equals 16, well, then we'll jump to that patch. We'll turn this into a convolutional feature map. Then we'll turn this patch into a convolutional feature map. And recall that a convolutional feature map is a learnable representation. In other words, an embedding. So we'll turn this patch into an embedding, this patch into an embedding, this patch into an embedding, and so forth. So let's see that in practice, hey? And you might be wondering, where did the idea of the conv2d come from? Well, there's one more thing that we're going to look at before we start to write the code to do this. And if we go down to the method, section 3, 3.1 is just a treasure trail of different ideas. There's this section here, hybrid architecture. So as an alternative to raw image patches, the input sequence can be formed from feature maps of a CNN. In other words, a convolutional neural network. So in this hybrid model, the patch embedding projection E from equation 1, if we go up to here, this is E, the patch embedding. This is what we're creating. We're replicating this section. We'll get to the class embedding and the position embedding later on, but we're just focusing on the patch embedding. So that's what it's referencing down here, is applied to patches extracted from a CNN feature map. So as a special case, the patches can have a spatial size 1 by 1, which means that the input sequence is obtained by simply flattening the spatial dimensions of the feature map. So that's where the flatten layer will come in. We'll see that in a later video. Of the feature map and projecting to the transformer dimension. The transformer dimension is from table 1. And then the classification input embedding and the position embeddings are added as described above. So what it's saying is that we can create these using a convolutional layer, and then we can add these, the X class embedding and the position embedding later on, which is what we're going to do. So let's, one more time, have a look at this. Visualize, visualize, visualize. Here's what we're doing. We're going to original image. We're going to cut it into patches. To turn each of these patches into an embedding, we're going to apply a convolutional layer. And we can set the kernel size equal to the patch size. So the kernel is going to create, and then the stride to the patch size as well. And then the convolutional layer is going to turn each patch into a learnable feature map, or in other words, a learnable embedding. And then we can flatten to a sequence, and that is going to be our patch input embedding. There we go. Let's start to write some code, hey? So I'm going to jump into here. And so let's go create conv2d layer to turn image into patches of learnable feature maps. And this is embeddings. So patch embeddings. Now, how might we create this? So of course we can just do it like we've done before. From torch import nn, and then we're going to set the patch size. So patch size equals 16. And then let's create a conv2d layer with hyperparameters from the vit paper. So we'll call this conv2d equals nn.conv2d. In channels is going to be equal to what? 3 for color images. And then we're going to have out channels, which is going to be equal to what? Well, I'm going to set this to 768. Now, where did I get that from? So this is D size from table 1. So that's the embedding size. So when we run our convolutional layer over our image, it's going to have a kernel of 16 by 16 and a stride of 16, but we wanted to turn this patch into an embedding size of 768. That's where that number comes from. So let's keep going. Oh, table 1, sorry. We can go back up to table 1. 768, hidden size D. And if we wanted to replicate a different size model, we could use another value here if we wanted to. But that's the beauty of creating it like this. We can just set that value just like that. Then we can go kernel size equals patch size. And then we can go stride equals patch size. And then padding we're going to set to 0. So let's have a look at our conv2d layer. Wonderful. So it takes in channels of 3 a color image, out channels is 768, which is our embedding size, a kernel size of 16 by 16, and a stride size of 16, which is exactly what we want. So let's keep going. We'll visualize a single image. View single image, just to remind ourselves of the image that we're dealing with. Plot im show, image.permute. We'll go 1, 2, 0, and then we'll go just to make sure the dimensions are compatible with matplotlib. We'll set the title to class names label, and then we'll go plot axis false. So I think my current image is of sushi. Oh, it's of steak, excuse me. And then of course, if we reran all of these cells, we'll get a different image here. Now, while that runs, what should we do next? Well, of course, we want to pass our image through the Conv2D layer. So pass the image through the convolutional layer. So how can we do that? Well, we can go image out of conv equals conv2d image.unsqueeze. We have to add a batch dimension here. Add batch dimension, because that's what our conv2d layer is going to be expecting. So this is now going to be an image of batch size, color channels, height, width. And then we want to go print image out of conv, and we'll get its shape. Beautiful, look at that. So we have a batch size of 1, and then 768, where does that come from? That's our dimension, so our embedding dimension. And then we have 14 by 14. Now, where does that number sound familiar from? 14 by 14. 196. So that is our number of image patches. So how do we get that into this dimension? Well, if we go back to our visualization, let's just rewatch this again. So our original image, we'll cut into patches. What we've just done is cut our image into patches, and we've applied this convolutional layer. So we've set the kernel size equal to the patch size. So we've got a patch, and then the stride is also equal to the patch size, so it jumps to the next patch, and it creates feature maps here, which are learnable representations of each patch. Now, if we wanted to flatten to a sequence, well, we can use the torch.nn.flatten layer. So that might be an extension that you try for the next video. So give that a shot. You can read forward if you like. But now we've got a learnable representation of our image in the correct size that we need. But we just need to flatten these outer 2 dimensions. So instead of being convolutional feature maps, we have a flattened sequence, which is what it states in here. So as a special case, yeah, here we go, which means that the input sequence is obtained by simply flattening the spatial dimensions of the feature map and projecting to the transformer dimension. So give that a go. We want to flatten these 2 outer dimensions into one single dimension and get 196. We'll try that in the next video. I'll see you there.